Hello everyone, I'm Nick and we are going to do some maths today. What's on the programme? We're going to delve into the realm of further statistics with some chi-squared. Let's dig in. So we're going to put the question up on the screen here. Take a second, pause the video to have a little bit of a read if you need to. All right, let's delve into it. So what have we got? A factory wants to investigate what's going on with how many defective pins they have in batches of 6. To do that, they take 40 of those batches and count how many defective pins there are. And they recorded their results in this table. So of those 40 batches, 19 of them had no defective pins out of 6, 11 had 1 defective, 7 had 2, and so on and so forth. Now what the question is saying is that they think this could be modelled by a binomial distribution. That is what we are going to investigate. Now, if you remember, part A said show that the proportion of defective pins is 0.15. Let's start with that. All this means really is let's find the average. So how many defective pins were there? There were, so for part A, there were 0 times 19. 11 lots of 1, 7 lots of 2, 2 lots of 3, no lots of 4, 1 lots of 5, 0 lots of 6. So that gives me how many defective pins there were and how many pins did we check in total. Well, there were 40 batches of 6, so that should be 40 times 6. Let's check this out. I know you've all tuned in to see a grown man type numbers into a calculator. That's what everyone wants. 11, 14, 6 and 5. Divide that by 240 and we do get 0.15. Excellent. Right, step 1 done. Step 2. They think it should be modelled by binomial distribution. Okay, fine. So what we're saying is essentially, let's break this down, is that each little batch of 6 follows the binomial 6, 0.15. And what we want to know is how many out of those 40 batches we would expect to have no defective pins. 1, 2, 3, 4, 5, 6. Well, let's start with 0, for example. How many would we expect to have 0 defective pins? Well, we would take the probability that any given batch of 6 pins has no defective ones and times that by 40. And that will give us, if we do that, 15.085. And in fact, what we're going to do is we are going to create a new line in our table called the expected frequency. The expected frequency. So we would expect 15.085 with 0. In fact, let's round that to 1, 15.1. That's probably plenty for now. I'll just keep track of the numbers in the calculator. And we can do the same exercise for all of this. All right, so this is the probability of any batch having none of them. What does that mean out of 40 batches? Times it by 40, which tells me about 15.1 of them should have no defective pins if the number of defective pins follows this distribution. All right. What we're going to do is do the same thing for all of these. I've rounded all of these to 1 decimal place. That might be a bit excessive, but there we go, 0.2. And basically both of these, I'll give that one 1 extra decimal place. We'll go to 1 sig fig there and 0.0005. So none really there. Okay. Remember, how do we compare expected numbers to observed numbers? That is where chi-squared comes in. A little reminder for us that our chi-squared statistic, the one that we are calculating, not my best chi ever in the history of the world, is the sum of the observed frequency minus the expected frequency, let's index those over I, squared, and then rescaled over the expected value. All right. Now then, where does that take us? The question says that they have a test statistic of 2.689. The question told us that you could sit down and calculate this. But before we do that, we need to have a little think about what we're doing. If you recall from your lessons, from your textbooks, wherever you've learned about the chi-squared before, what we know about this distribution does require these to be big enough. The expected frequencies need to be big enough. Now, what is big enough? We need the expected frequencies to, in fact, be bigger than or equal to 5 as a rough overall. 5 is the general consensus of when this works. So, as we can see, in fact, these are really small. And the reasoning behind that is that we are trying to get a measure of how wrong our numbers are, right? How wrong our numbers are. But because we're counting, if the expected number is too small, then in fact, any amount of error is basically negligible. If you're expecting 0.2 of an item and you get 0 or 1, I mean, is that so out of place? Not really. It's too small for us to measure the difference. So what we're going to do is we are going to smush all of that together. We're going to smush it all together. So which ones do we need to group to get at least 5? We're going to start grouping them. So 6 and 5, not enough with the 4. So what we are actually going to have to do is we are going to have to group all of these. We're going to have to group all of them. So what we end up with is this, the number of defective pins. We're only going to look at the cases 0, 1, or more than or equal to 2. We're going to go for O for our observed frequency, which was 19, 11, and then that should be 10 in total. So 10, I need to make sure, let's make that readable, that 19 plus 11 plus 10, that should come out as 40. There are 40 batches of pins that we've looked at, and our expected frequencies here, 15.1, 16.0, what's that together? 31.1, so I reckon that comes out at about 8.9. Now, if we do this, we will get our calculated, let's see if I can make, oh, that's better. If we figure this out, our calculated value should be 2.689. Bear in mind, I've rounded these a little bit more just so I can fit them on the board. Ideally, we'd have a couple more decimal places in there, but I have limited space. All right, next step. We need to be able to check what our critical value is. All right, so that is our measure of how wrong our numbers are. That gives us an idea of just how far apart our expected numbers are from our observed numbers. We need to compare that to something. What are the odds of this being true? What are the odds of that happening? All right, so let's lay out for ourselves a hypothesis test. Let's lay out a hypothesis test for ourselves. Let's go over here. Our null hypothesis is that the binomial is a good fit. Our alternate hypothesis is, funnily enough, is not a good fit. And we are comparing this number to some probability distribution. Luckily for us, we know what the distribution is for chi-squares. You don't need to know the ins and outs of it. It's to do with the normal distribution. And basically, it's always a one-tailed test. If this number here is too big, if this is too big, then we would conclude that these numbers are too far apart overall, and therefore this is probably not a good fit. So this is always a one-tailed test. Now we need to know how many degrees of freedom I have. New. Degrees of freedom. Always a difficult topic for people to get their heads around. That means when I fill in this table, how many of those numbers could I choose? I mean, realistically it's these, but there's a couple of things that get simplified. Well, I've got three choices for these. Really it's these, but I've got three numbers I can fill in. The 0, the 1, the more than 2, right? However, as soon as I fill in two of them, the third one is fixed in place because the total has to be 40. Same for these ones, once I've filled in two of them. So I need these two totals to match, because no matter what, my total observed batches and my expected batches needs to be 40. Otherwise, I'm comparing two different things. So already, my degrees of freedom is 3 minus 1. I've already lost a degree of freedom. I can only choose two of these numbers. But we actually lose another one. Why? Where did this 0.15 I used to calculate these from? Well, it came from this data. So in fact, I lose another degree of freedom because when I choose these numbers, or these ones up here, I need to make sure that the average proportion or the overall proportion of defective pins comes out as 0.15 as well. So the average proportion of defective pins is 0.15 for the observed frequencies and for the expected frequencies. So in fact, we lose another degree of freedom. So what that means is I only have 1 degree of freedom. There is only one number here that I can choose before the other two get fixed in place. You can think of it either as choosing the observed or the expected. That doesn't really matter. But in any one of those two cases, I get to choose 1 out of the 3. The other two get locked in by the fact that the total is 40 and the proportion, the overall average number of defective pins is 0.15. I'm now ready to go. I can go look up in a table or my calculator, however you choose to do it, depending on your exam board, the resources you have, what devices you have. But we can find that the critical chi-squared value, the question, if you remember from the setup, wanted a 10%. All right, so it's a critical value at 10% for 1 degree of freedom is 2.706. All right, and remember, our calculated number was 2.689. Do we reject, yes or no? The chi-squared distribution looks a slightly skewed normal, something like that. It doesn't really matter. But if I want to be in the top 10%, I would have to be at 2.706. Our value is 2.689. We are not in the top 10% of values. We are not in the 10% least likely values to happen, i.e. this number is reasonably big difference, but crucially, it is just shy of my cutoff point. So what do I conclude? I reckon that actually, all things being equal, there is insufficient evidence to reject H naught. All right. I probably need to write down here somewhere that 2.689 is less than 2.706. And we put in a nice conclusion within context. We conclude that this suggests that the number of defective pins does follow a binomial distribution. And there we go. Not too bad. All right. There was a part C. We might have to pop it back up on the screen for a second. Screenshot if you need to. What's the question asking us here? What if actually we got our numbers slightly wrong? What if we got our numbers slightly wrong? And I'm going to actually have to get rid of that line. And in fact, our new observed, or our actual observed frequencies were 19, 11, 6, 3, 1, 0, 0. So we mismeasured somewhere in there. And the question is, what will that do to our hypothesis test? What will it do to our chi-squared statistics? Well, actually nothing at all. Our answer is going to be, it will make no difference whatsoever, because the numbers that get moved around, well, fundamentally, are all in this zone here that we smush together anyway. So when I put it all together into this table, I will still get 19, 11, and 10. So our answer is, what difference will it make to the hypothesis test? None whatsoever. All right. I think that takes us to the end of this question. Quite a bit to think about and a couple of pitfalls that you can fall into. Number one, forgetting to make sure that your expected frequencies are all at least 5. Very common mistake. And then being very careful about how many degrees of freedom. All right? Don't fall for it. I hope you found that interesting. I'm Nick. This was a bit of further maths. Don't forget to go check out the TikTok. We've got videos daily coming out on there that you might find interesting. In the meantime, I'll see you around.